So today we are going to start with the second part of first module, that is metal oxide semiconductor field effect transistor. Specifically we are going to study the N channel MOSFET, and basically we have two types, P channel and N channel. So we will be studying N channel MOSFET. To start with the structure, just to see this diagram, we have a P type of substrate. P type means it is a what do you call, you have already studied PN junctions, okay. So this is a P type of substrate, and inside that we have two N type of materials. We are denoting it with N plus and N plus here. That plus indicates the N materials are heavily doped, whereas P type materials are lightly doped. That is, compared to this P type, the N type materials are highly doped, okay. And the red pen indicates the metal contacts which have been taken out for connections, right. So this is the connection for N channel, this N channel, this is the connection for this N channel, and in between these two N channels we have a metal which I have drawn it with a blue ink, and on top of that again you have a marked with a red ink, again it is going to be a metal, okay. And this portion is denoted as gate, this portion is denoted as source, and this portion is called as drain, okay. So that is, this N plus is the source terminal, this N plus is the drain terminal, and in between this metal part is called as the gate terminal, okay. Now this we call it as the body, that is P type of substrate, and even for this body there is a metal for connection, there is a metal provided. So this is called as body, which is denoted by B, okay. And this space in between these two N channels we call it as the channel region, fine. So basically in between this metal and this channel region, this portion is of the oxide, that is silicon dioxide, which has a specific thickness of TOX, okay, which is going to be typically 2.50 nanometer square, that is very thin layer of silicon dioxide, okay. So that is why it is called as a metal oxide semiconductor. This is the metal, this is the oxide, and this is the semiconductor part. So that is why the structure is called as metal oxide semiconductor, and the channel which is going to be formed between these two regions is going to be of N type. That is why it is called as a N channel MOSFET, okay. Okay, so with that structure we will just see how it operates, fine. So without connecting any supply voltages, that is no bias voltage is applied to the gate, okay. So that is, just refer to this diagram. Here I have shown the VGS, but now for this section you assume that this supply is also not there. So we are not applying anything. Here also it is grounded, VG also is grounded, this is also grounded. So it is just going to be a two PN junctions. One is this junction, PN junction, another is going to be this PN junction, that is without applying any voltages, or without, or what we call it as operation with no gate voltage. So it is just a two PN junction. This is one PN junction and this is one PN junction, okay. So as we know, when you have a PN junction, there is going to be a depletion region formed, okay. So this is denoted by depletion region here, fine. Now as we already said, the N type materials are heavily doped and P type materials, this is lightly doped. The depletion region is going to be more in this region and very less in this region, okay. I repeat, it is lightly doped, it is heavily doped. So the depletion region here is going to be much, and it is going to be very less in this region. So it is not, or negligible, so it is not shown. So this is going to be all this is going to be the depletion region, which has immobile charge carriers, okay, which has immobile charge carriers in between. So that behaves as a high resistance, okay. So that behaves as a high resistance, that is what it is written here, okay. So this is like connecting two back to back diodes. This is one diode, this is one diode. Now even if you apply any voltage between drain and source, this path is going to provide a very high resistance of the order of say 10 raised to 12 ohms. So there is no current, there will be no current flowing in this path, okay. So that is the operation with no gate, fine. In the next part we will see how we can create the channel in between. Now for this case, this channel is also not there. This channel has to be created. Now we will see how it can be created. Now to create the channel, what we will do, again this source is connected to ground. The gate is supplied with a voltage like this, plus minus. Now this is denoted as VGS. Since S is also grounded, this is also grounded, so we denote it as VGS for the gate terminal. Drain is also grounded. This is N plus, like this the structure is there. So when you apply the VGS here, what happens? There is going to be a positive charges created on this metal. Because of those positive charges, it attracts the electrons from the p-type of substrate, okay. Now p-type material means there are going to be some minority charge carriers also, okay. P-type substrate, holes are majority charge carriers. Along with the majority charge carriers, you are going to have the minority charge carriers that are nothing but the electrons, okay. So when you apply plus this type of supply here, a plus will be created here, and that attracts these electrons, negative charge carriers from the p-type substrate. Also if you just see here, N is connected to negative, this is also connected to negative, and this terminal is positive. It attracts the carriers from this N region also, it attracts the electrons from this N region also. So along with all these, they all accumulate at this region. What are those? Minority charge carriers from p-type, some charge electrons from this part, some electrons from this part. All of them move towards here and they form a, or what we say, they accumulate in this region and they form a channel, okay. This we call it as the induced channel, which is going to be of length L, okay. So this is very important to create a channel. So the length of the thickness of this channel is going to depend on the amount of VGS what you connect. More the amount of VGS, more thick is going to be this channel, and more current is going to be flowing from drain to source, okay. So lower the value of VGS, the thickness is going to be lower, lesser current flows from drain to source, okay. Now initially when VGS we start from 0, if we go on increasing it till it reaches a certain value, channel is not going to be formed, okay. So there is one threshold value which depends on the construction of the MOSFET, fine. So unless VGS crosses that threshold voltage, channel is not formed, okay, and that voltage we call it as the threshold voltage, okay. So that is what we define here, the value of VGS at which a sufficient number of electrons accumulate in the channel region to form a conductivity of channel is called the threshold voltage and denoted by VT, fine. So your VGS value has to cross the value of VT to create this channel, fine. So this is creating the channel for the current flow. Now once we have created the channel, we will just try to plot a graph, okay, of ID versus BD S, okay. So I start with, so this curve is VDS. VDS is the voltage applied between the drain and source, that This is ID. So you just see, this is for VGS less than VT. Okay, VGS less than VT. What you observe is current is almost 0. This is current axis. So VGS is less than threshold voltage, so no current, almost 0. Okay, so now I increase VGS to more than this, that is VT plus 0.5. VT plus 0.5. So what you observe? The current ID increases. Next I increase VGS more, that is VT plus, I increase it 1 volt. So again we see there is more drain current flowing, that is denoted by ID. ID we call it as the current from drain to source. Fine. So here again I increased VGS, more drain current. Here I again increase VGS, there is more current. So what we observe? More the value of VGS, more the thickness of the channel is going to be, more the current is going to flow from drain to source. Okay. So what we conclude here, for a MOSFET to conduct, the channel has to be induced. Okay. So unless you create a channel by supplying VGS, the channel is not going to be created, so it will not conduct. Okay. So we have to create a channel, or we have to induce the channel. Then increasing the VGS above the threshold voltage VT enhances the channel. Okay. So as you supply more and more VGS, you are going to increase the width of the channel, or you are going to enhance the channel. Okay. Hence it is also called as enhancement mode operation, or it is also called as enhancement type of MOSFET. Okay. So that is one part. Next we will see. Now in the previous part we just studied after applying VGS what happens. Now what we will do? We will connect another voltage between drain and source. Okay, drain and source. As it is, this source is again connected to ground. Here again VGS. Here again we are connecting one more VDS, which causes the current ID to flow. Just see the direction of ID. ID flows like this. Okay, it goes here. Now we have provided the channel. It passes through the channel. Okay, and it goes to source. Okay, so from drain to this drain, this channel, this source, and it ends here. So here it is going to be ID, and here it is going to be IS. So IS is obviously going to be equals to ID, and IG is going to be 0 because we have the insulator material of SiO2. No current flows in this terminal. Okay, why is it so? Because we have the insulator in between this metal and this channel. Okay. Fine. So we have number of cases here. I'll just explain one by one. So when you make VGS is equals to VT. Okay. So what happens? The channel is just induced and current conducted is very small because it has to cross VT. Okay. So we are providing some fixed VDS here. We go on varying VGS. So initially let us say it is equals to VT. Channel is just induced, so very small negligible current flows through the channel. Next, as we go on increasing VGS, as VGS exceeds VT, that means it crosses the threshold, more and more electrons are attracted to the channel. So channel is formed. Okay, so more charge carriers in the channel. Okay, as the channel depth or width increases. Fine. So what we say, the conductance of the channel is proportional to excess gate voltage. Okay, so that is excess. Up to VT it is not conducting. Above VT whatever we are providing. Okay, so it is proportional to that. So that is denoted by VGS minus VT. Okay, so the conductance of the channel depends on what voltage? VGS minus VT, which is also known as effective voltage or the overdrive voltage. Fine. So the current ID will be proportional to VGS minus VT and of course to the voltage VDS. Fine. So what is it? VGS you start with, make it equal to threshold. So very small current. When VGS crosses VT, whatever above VT you are providing, according to that your channel builds up. Okay, and according to the current ID flows. That is why we say the conductance of the channel depends on the excess voltage what you are applying, which is given by VGS minus VT, and it also depends on VDS, right? So this is the case of applying a very small VDS. Okay, so now we go for the next case. Now what we do, we are going to study the next case when we make VDS variable. Now we will fix VGS, and now we go on varying VDS and just see what happens. Okay, so as I said, we are going to fix VGS and then we are going to vary the VDS. What happens now when VGS is less than VGS is greater than VT, channel is formed already, okay, and some VDS is applied. So what is happening? Just see here, VDS, just refer to this graph here. Okay, so we have VDS on the x-axis, we have ID on the y-axis. Okay, so we go on increasing VDS. Our VGS is fixed. Okay, so that is VGS is fixed at more than VT. Fine. So we go on varying VDS. So VDS, as VDS increases, the current ID goes on increasing. Okay, as the value of VDS reaches the level of VGS minus VT, okay, as the level of VDS increases to the level of VGS minus VT, okay, what happens? The current saturates. Initially it is increasing like this, and as the VDS reaches this value, that is VGS minus VT, okay, the current saturates. Saturates means it almost remain constant, no increase. Fine. So this region we call it as saturation region, where VDS is greater than or equal to VGS minus VT. Now this initial region we call it as the triode region, where VDS is less than VGS minus VT. Fine. So here it is written current saturates, and because the channel is pinched off at the drain end and VDS no longer it affects the VDS no longer affects the channel. Okay, so just see in the diagram what happens. As you go on increasing VDS, the channel shape becomes like this. Okay, let us not go into more details of it because the explanation is too lengthy there. Fine. So as you go on increasing VDS, the channel becomes like this. Okay, it gets tapered towards the drain, and that makes the ID current to saturate. Okay, that makes the ID current to saturate, and this voltage VDS saturation is going to be equal to VGS minus VT. VT is going to be fixed for the which comes fixed value for one particular MOSFET which depends on the manufacturing techniques. VT, VGS is what we are applying here. Okay, and we go on varying VDS. So when it reaches this value, this becomes saturated. Now this graph is for one value of VGS, one fixed value of VGS. Now what I will do, I will increase VGS to another level, next level, then again I go on increasing VDS. Then what you observe? What you observe? So the current VGS is increased, so obviously the current is going to be increased like this. Okay, again it is going to be at some value it is going to saturate. So what you observe here is, as you go on increasing VGS, the saturation ID increases. Now for particular VGS, this is your saturated ID. I increase VGS, it is going to be somewhere another curve like this. So this is going to be another ID saturation value which is more than this, right? So I increase VGS, again it is going to be like this. One more, it saturates at another value of ID. So when you compare this ID and this ID, you observe that ID goes on increasing as your VGS value increases. Okay, so the current ID is controlled by what voltage now? It is controlled by VGS. Okay, that is why these devices are called as voltage controlled devices. Okay, voltage controlled devices. You go on increasing VGS, your saturation value of ID is going to be more and more, or higher and higher. Fine. So your output current, that is ID, is going to be depending on the value of VGS. Fine. So this is the explanation. So we have two equations here. The derivation is not necessary for you. Fine. Now, as I said, the device is operated in two regions, the triode region and the saturation region. Okay. So always the MOSFETs are used as amplifiers in saturation region, and they are going to be used as switches in the triode region. Okay. So understand this. The MOSFETs are used as switches in the triode region, whereas they are used as the amplifiers in the saturation region. Okay. So the current ID will be given by this equation here. Just see, ID is Kn dash W by L, VGS minus VT, VDS minus 1 by 2 V square ds. This equation is for triode region. This equation is for triode region, whereas in the saturation region ID is given by half Kn dash W by L, VGS minus VT square for the saturation region, where Kn dash is given by mu n into COX. Okay, where mu n we call it as mobility of electrons, and COX is given by epsilon naught x divided by TOX. Okay, so epsilon naught x, this O stands for, OX stands for oxide here. Okay, so the epsilon naught is permittivity of the oxide material used, that is silicon dioxide, and the thickness of the oxide material. Okay, so it is epsilon naught x, which is given by 3.9 into epsilon naught for a particular silicon dioxide. So this is its value, and thickness again it depends on the construction of the material, which is typically is going to be of 10 nanometer. Okay, W is called as the width of that silicon dioxide material, L is the length. This is here. See, this one, length is this, and if you just, this is the diagram we are seeing like this. Okay, so it has also got some surface like this, okay, where it is going to be denoting the width of the material. This represents L. So if you just see top view, there is going to be some width for this channel, this oxide material here, and that is denoted by W. So that is what given in this equation. Okay, so this is the width and the length. Okay, let me tell you, all this is not there for your syllabus, but your syllabus starts with biasing of the MOSFETs, but since you don't know much about the MOSFETs, I have just given you the introduction. You should at least know how this works. What do you mean by source? What do you mean by drain? What do you mean by gate? What do you mean by channel? And what are the currents ID, VDS, VGS? Okay, so without knowing all these things, you don't understand the next part. As I said, this is not there for syllabus. Still, what you do, you copy these notes into your book, listen to the video once or twice, make this part clear. So I will give you next video by tomorrow evening. Okay, so by that time you study it and make yourself clear with these concepts. Okay, and other than that, just give me the feedback, how you felt. Okay, you want some improvements, or is it okay? The visibility, the sound, if it is clear for you, I will continue with the same thing. If you want me to improve something, you are free to give me the feedback, so that I can I can incorporate them in the next video. Fine, thank you.